In this lesson, we're going to continue to build the conceptual conception that derivative means slope, right? Specifically, it's the slope of the tangent line or the rate of change. The way we're going to do that is mostly by examining graphs, and they're mostly going to be linear graphs because those are graphs you guys are already going to be familiar with. We're going to look at the derivatives of these and how they work out graphically. So first of all, let's just think about this for a second. So we have a y equals mx plus b line. What's the derivative of y equals 3x minus 5? Well, if derivative means slope, then the derivative, we'll call it y prime, is 3, because that's the slope of my function. Slope is my m, right? So if I ask you here, in this first example, to graph this function's derivative, notice we have 1, 2, 3, 4 line segments. What it's really asking me to do is graph the functions. Okay, so you guys know how to find slope. Maybe we can take a second to find the slope of each individual line segment here. Here are my slopes that I'm finding, and I'm just doing rise over run, right? So I'm doing rise over run, change in y over change in x. If this is f of x, we're going to call our second graph f prime of x. And this is going to be a graph of our derivative. So from -4 to 0, my derivative is 1/2. And that's a horizontal line because if this is a function, y equals 1/2, that's what that function would look like, right? I'm going to make open circles at the end, and we'll talk about why that is in a second. From 0 to 1, my slope is -4. And then my slope is 0, right, because it's a horizontal line. From 1 to 4. And then from 4 to 6, my slope is +2. Okay? So this is the graph of my derivative of this function made up of line segments. And notice they're all horizontal lines because my slope is always constant, right? So on a line segment, your slope never changes. And then the second question, question B, this gets to these open circles now. When is the function not differentiable? Not differentiable. Differentiate means to take the derivative. Not differentiable means the derivative does not exist. And notice at these sharp points here, it doesn't make sense to talk about the derivative because we can't talk about the slope here. Like I can draw a million different tangent lines to one of these points. That single point doesn't have a slope. So we'd say x equals 0, x equals 1, and x equals 4 because it has sharp points. Okay? And that's why I drew open circles here to represent that the derivative does not exist. That really makes sense if you think about the fact that the derivative is a limit, and the limit has to be the same on the left and right in order to exist, right? So the derivative does not exist at those points. Okay? Now, let's put this in context. We're going to use an example here. And the example is about driving at a certain speed. I know I'm using these examples a lot. It's not because it's the only ones I can think of. It's because it's really easy to wrap your head around. So we'll look at different applications when we're a little bit more comfortable with the concept. So here's what we're doing. We're driving away from home at a rate of 40 miles per hour for 2 hours. Then we stop 1 hour for lunch. And then we drive back to our home at 20 miles per hour. So we're going to graph of x of t. We'll call this x of t. Our position, and then x prime of t is going to be our velocity. And we'll make our scale 10 miles per hour, or 10 miles per box, I should say. So 10, 20, 30, and so on. So suppose we're driving away from home at a rate of 40 miles per hour. Well, that means in 1 hour, I travel 40 miles, right? And then my second hour, I'm 80 miles away from home. Okay, so I get a line segment up to here. And then what happens? I stop for an hour for lunch. So that's 1 hour where I'm not traveling, right? My distance is constant. And then I drive back home at a rate of 20 miles per hour. Well, that's the slope of -2 on my scale, right? So there's my distance graph. And then I end up at home at 1, 2, 4, 5, 6, 7 hours it takes me to get back home. Right? My velocity graph is then going to be the slopes of each of these little line segments. So my slope is 40 miles per hour for 2 hours. 0, right? Because my speed is 0 when I'm eating lunch for an hour. And then negative 20 miles per hour because I'm going downhill. So we'll make our graph a little bit longer here. We'll say negative 20 is my slope here. And we're going to do the same thing we did before. We're going to do open circles at the end to represent that the derivative does not exist at these sharp points. We have 40 miles per hour, 0, and then negative 20 miles per hour. And then negative just represents that we're going the opposite direction. So x is hours in both. My y-axis here is miles. And then my derivative, x is per y. Or sorry, y is per x. So miles per hour. Right? That makes sense because that's how you measure speed anyway. Okay. So you could have probably done this without ever understanding the derivative. What we're building towards is being able to connect these graphs for curvy functions. So you already are really familiar with linear slopes. We're building towards slopes of functions that are not linear. So let's look at a simple example of that. It's a great time to make sure your notes are complete before we move on. Okay, so here we're looking for the tangent lines to my parabola here at 1 and negative 1. All right, so we're going to use the limit definition to find the derivative, right? So we have x squared is our function. You should be good at this by now. And then my x squareds cancel out. And then I'm left with a limit with only h's in top, which means I can cancel out my h. I should be quite pleased with that. My derivative is 2x. Okay, so f prime, the derivative of f, is 2x. By the way, we're going to learn a shortcut for this in the next lesson. So if I want the tangent lines at these two x values, I'm going to go ahead and plug those in, right? So f prime of 1 is going to be 2 times 1 is 2. F prime of negative 1 is going to be negative 2. And then I need points, right? So y equals 2x plus b, and I'm going to plug in a point. My point is going to be 1, comma 1 squared, which is 1, 1. And I get 1 equals 2 times 1 plus b, right? And that means b has to be 1. So my first tangent line is y equals, I'm right over here because that's where we're going to draw it, y equals 1x plus 1, all right, 2x plus 1, and that's going to look like, so slope of 1, more or less going through this point 1 comma 1, notice my scale is by 2's here, and then my second tangent line at negative 1 is going to be at the point negative 1 comma negative 1 squared, which is also positive 1. So I'm going to get y equals negative 2 x plus b, and I'm going to plug in this point, and I get 1 equals 2 times negative 1 plus b, and that gives me b equals negative 1 as well. So I get two tangent lines that look very similar. They're mirrors of each other, right? But what we notice is as the function is increasing, my tangent line has a positive slope. As the function is decreasing, my tangent line has a negative slope. And that is really the crucial key takeaway here. As I look at my graphs down here, notice, this by the way is my derivative, f prime of x equals 2x, which you know is a linear function through the origin. This is, notice, decreasing to the left of 0, increasing to the right, negative to the left of 0, positive to the right. So that is the relationship between the graph and the derivative. Is that the derivative being positive is equivalent to saying the function is increasing, and vice versa. So that is what's going to allow you to connect the graph of a function to its derivative.